Welcome to another video explaining the universe using the particle model. Well, in my last video, I proposed that I was going to do an experiment with G1 speed, G1 particle speed through a resistor and analyze the current. But first I've done the calculations to see what the particle model would predict. So this is a video on the calculations for the G1 speed versus current. But first we'll do a video on the book that my son and I have written. Yes, the book is titled Principia Mathematica 2, and it is available from Amazon, and you can buy a hardcover book now for $41.99, paperback for $34.99, and the ebook for $2.99. Or you can go to a simple link on Amazon, tpm.thehilster.com. That's an easy link to get there. So if you get an opportunity, you can't afford the paperback or hardcover, the ebook should be very reasonable. Well, I've been going through a bunch of list of words, and part of the words that were anomalies was one. Equation was another word I've been doing, and of course this one is about the equation for the current through a resistor when you take the speed of G1 into account. If you have a question, any question at all, ask Particle. You can do that by emailing me at particleguru@gmail.com. Well, what is this about G1 speed? As G1 current, that's like electron flow as opposed to a typical traditional current that flows around a circuit from plus to minus. G1 current flows out of the battery from the negative end and goes around the other way. And as this G1 current increases, the F2 force around the resistor increases, which increases the average speed of the G1s through the resistor. Increase in current, increase in speed. An increase of speed causes the G1s to pass through more easily. This theory helped explain the IV curve. That's the current voltage curve of the diode in that transistor. And a while back, I had two videos, one on the physics of the diode, the other the physics of the transistor. And I'll list these in the description of this video so you can get to them easily. As the G1 enters an object, it speeds up, and as it leaves, it slows down. That's a typical thing that happens with the TPM model. That's something that is not described in the modern science. And this is true of all level 1 objects. G1s can pass through level 1 object and in fact acts gravitationally on them, but G2 does the same thing, but then it does that same thing for level 2 objects. Okay, so this is the two graphs, so two IV curves, and I explained in the one on the IV that this would normally go straight out this way, except something causes the curve to go this way. And I explained that was caused by speed. You got the same thing here. You got the curve going straight up, but then it bends over and that way. And again, that's caused by speed. So I was thinking initially that, okay, I'll just take these are resistor curves, the IV curve for a resistor, and they're all straight lines. That's present day thinking. They're straight lines. That I added this thinking, well, it's gonna happen like the diode. Maybe it happens the other way like the transistor, but it turns out when I did the calculations, the resistor doesn't change. The equations, once you assume what the value are in the calculations or you measure them, it stays. The speed of the G1 doesn't change the value of the resistor. So this graph is wrong, so I had to find a different way to explain that. Well, this is the circuit I'm going to use and the circuit I set up to do the calculations with. I have an adjustable DC power supply. I show it here as a battery, but and I have two sensing resistors. These are like shunts. Right now, my plan is for 1.5 ohm here and 1.5 ohm here. Then I'll put any number of different resistor values here. You adjust the battery voltage, the power supply voltage, to increase the current, and then you measure the current here, but you measure the voltage, divide by that, you get the current. Measure the voltage, divide by this, you get the current, same way. So you can get the current here, here, and here, and the object is to see, as you increase the voltage, you increase the current, what is the effect on the current around the circuit? That's the G1 current. So there are standard equations. This is something you learn in high school, college, on any video. The total current around this circuit. Now, normally they talk about current this way. The total current is the battery voltage divided by the sum of all the resistances. These are all resistors. It's just very small shunt resistor. And that current is labeled I of t. Well, you can also get the current around this by measuring the voltage of the S1 and divide it by the resistance of the S1, and you get this current. And same thing for R1, same thing for S4. And the fact is, however, what they show you is that are all equal. It's all the same going around that circuit. That's the standard model. Now, TPM says differently. TPM equations without speed. I've done this, shown these equations many times. I use a spreadsheet to do the calculation. You set A to any number, and B is equal to A coming in plus the voltage of the battery divided by VG1. And these are the values I typically use for VG1 and IFR. I've determined through a previous video that the product of these two is generally around that value. And I picked 0.1 volts per G1 as a standard, and you then can take this number, divide by VG1, you get IFR, and it's just a factor of a power of 10 off. So you write the equation for the loss of G1s through here, and the loss is B times the resistance S1 times the interaction factor times this. And B1 is equal to B in minus the B loss, and you get B1. C is equal to B1 in minus the loss through the resistor, and the same for that. And when you finally get C1 at the end, you start the next cycle in your spreadsheet by setting the value of A to the previous C1. In the TPM model, the battery adds G1s and the resistors lose. As a consequence, the number of G1s flowing around this way should be higher here, fewer here, and that changes the current. It doesn't make it the same all the way around. That's the prediction of the particle model. Well, this is just a repeat again now. I'm going to add speed to it. I'm going to go through a little bit about how I accommodate the speed as it goes through the resistor. Okay, the adjustment for speed. Without speed, the loss through the R1, which is I'm primarily interested in, although I did do the loss through S1 and S4, the loss is the number into the R1, which is B1, times the value of R1 times the interaction factor. This value is reduced as B1 increases. So there is a reduction caused by the speed. I'm going to call that now speed factor. I came up with this. There's a previous video I didn't list it here, where I came up with this term as a speed factor. M2R is the G2 mass of the resistor. Let me just say that's what it is. If the number of G1s going through the resistor is 0, the ratio of this is 1, and the speed isn't reduced at all. The particles that go through much more easily. It's the same as if there were, but you don't have any B1s coming through anyway. So the speed factor modifies, what it does is it modifies the interaction factor. Doesn't modify the resistance, doesn't change the number coming in. So this factor, speed factor, modifies the interaction, reducing the number that are lost. In other words, they more easily pass through. The higher the current, the higher the number of B1s. The fewer that are lost and more that pass through, and that changes the current through these resistors. Okay, what is G2 mass? I have to have some basis for G2 mass, and G1 mass is the Newtonian mass of a resistor in grams, which is caused by G1 gravity. Yeah, you can take a resistor, you can weigh it, and you can weigh it in grams, but that's not important to the circuit. But the resistor has a mass caused by G2 gravity and can be stated in units of G1s. This is a generalized theory of the mass of the G1 particle and the N1 particle, and I'm doing it in units of G1s. G2 gravity, for example, holds the hydrogen atom together and in place, holds the G1 around the N1. The hydrogen atom has one G1 and one N1. The G2 mass of the hydrogen is dominated by N1, which has a mass of about 2,000 times the G1. Actually, the number is like 1837. It's a typical number used by modern science to show the ratio between the electron and the neutron or proton. I rounded it off because my numbers are pretty much guessed at, so I'm rounding it off to 2,000. And so the G2 mass of the hydrogen atom is 1 N1, which is 2,000, and 1 G1, which makes it 2001. Yeah, so I could take a resistor, if possible, and try to figure out how many N1s and G1s are in that resistor, and I can tell you that's a tough goal. It's hard to really figure out something that make it that precise. So I did it a different one because what is the G2 mass of the resistor? I don't know. The expected change due to speed is small, so M2R must be large compared to the B1. When you look at that equation, M2R over M2R plus B1, M2R must be large compared to B1. So at one point on a standard circuit without TPM, just 5 volts and the S1, the R1, and the S4, I find that at 5 volts, B1 is this number, so I set it to 100 times that. Literally, it's 100 times that, which means that the G2 mass of the R1, and I was using a 4K resistor for R1, is about 780 million G1s flowing through the circuit in 1 second when you power it with 5 volts. Amazing how many are flowing through. Okay, so now these are the equations for the circuit with speed. It's the same equations, only I put the speed factor here, the speed factor here, speed factor here, and what I just said earlier, that I made this number equal to 100 times this other number, and then when you increase the voltage and increase the current, you get a speed factor reduction, changing the current through all three resistors, S1, R1, and S4. Well, here are the circuit details that I used during the calculations. S1, S2 is 1.5 ohm. R1 is anywhere from 1K to 1 megaohm. When I do the test, I'll be using a larger range. I actually used 4K. I stuck with 4K in my calculations, but I did vary the voltage from 5 to 30, which is what my power supply can do. And yes, these are the same numbers I use in my calculations, and these numbers. And when I go to do the test, I have to measure all three resistances using 4-wire measurement, and then measure the voltage across each one, and then I can calculate the current. Remember, current is not real, it's a calculation. So those are the circuit details I used in the spreadsheet calculations. And here's the current I got for the standard model, where they say the current is the same all the way around. I only did the total. Here I'm only showing you the total. At 5 volts, it was 1.25 milliamp. This is minus e to the minus 3 is a milliamp. And this is literally, this is double, this is triple, quadruple, and so on. And I plotted it using the spreadsheet, and it's a straight line. The current all the way around the circuit, no matter whether it's IT or I of S1 or I of R1, it's all the same. And that's what they tell you, that's what they expect to get when you measure. It's just that they're all equal. Well, without speed, when I did that, now the TPM model, which says you get a little bit of loss as you go through S1, and then more loss as you go through R1, and more loss as you go through S1, you don't expect these to be the same. This is at 5 volts, current through the S1. Yeah, it's right about the same as 1.249. And I highlighted these three numbers because it's the only part of this calculation that changes. And sure enough, this is higher, and then this is less, and this is less. All the black digits are the same. Increase the voltage to 10. Now it does the same thing. It's higher, then lower, and now this is significantly lower. You have to look at 6 digits to see it, because this is 126, this is 118. So it still is higher, lower, lower, just like the particle model predicts. But it gives a big jump here on S4. This is where the compounding effect comes into place. S1 affects this resistance, and that's why it drops from here to here, because there's B coming into here, there's B1 coming into here, and B1 is less than B. So this is less. But S4 is affected by S1, and R1 affects S4. So this is a compounding effect. And it's a very little difference when you're at 5 volts, but clearly when you get up to 30 volts, you've got a significant difference between the two, but still, this is higher, then lower, then lower. Nothing strange. It's exactly what I have been saying for the 5 years I've been doing this. But here's the one with speed. when I introduce the M2R over M2R plus B1, when I enter that into the equation, affecting the interaction factor, making them pass more easily through, get a significant difference in the current. In this case, that's so significant, I'm highlighting the three most significant digits. This is 1.261 milliamps. That's higher than the other two graphs I've shown you. But when it gets to this resistor, it is in fact back down to 1.249. Yeah, so this is higher, this is lower, expected, but then this goes back up again. This is back to 1.261. This is easily measured in a sense with a 3-digit meter. I don't even have to have my 7.5-digit meter to see this, if in fact it turns out that way. I don't think it's not going to be that much, because I arbitrarily sort of picked the M2 mass of the resistor. That gave me very significant changes on the speed factor. If I got that number wrong, the changes may be there, but they may not be as dramatic as this is. I would expect it to be smaller. I made the number big enough so I could see the change in the spreadsheet. As a consequence, I get these numbers. And yet, all the way through here, this is higher, lower, higher. This is almost like it's nominal, but a little bit less than standard. And the difference is made up by this is a little bit higher here, and this is a little bit higher here. So you ask, well, how can that value go up? How can it be higher? Well, it turns out that the values around here, if you really look at the B values, and I don't have them plotted here, probably should have, they're very close. They don't change much. There's a base number A that goes around the circuit all the time. And the battery adds a little bit on top of the A. Then the resistors take that little bit away. But basically, so you've got a large value A and a small value B, that battery adds it and then reduces it, then reduces it. But this is a large number, 780 million at 5 volts. That's the number that's going through here, 780 millions plus a little, 780 million, a little bit less, and 780 million even more or less, but very fractionally small. So essentially, the B numbers are almost the same, and so that's why this particular jumps up. This reduces from normal because of the speed factor I put in. I put speed factor here and here, but the number I came up for the speed factor there was very, very small, hardly noticeable. So the reason that it went back up is because it's this number going in here is almost the same as this number, except for a small change. The other thing to point out is one of the reasons modern science says no, the current is the same, is that when they read the voltages, yeah, they almost look the same. Typically, you use a 3-digit meter. You see all the same. You don't see this extreme. That's why I say this is an exaggeration. The numbers are exaggerated. But the TPM model predicts that, yes, this will be a little bit higher, this should be normal, then that should go higher. So when I do the test, I'm not sure why I repeated this. Well, when I do the test, that's when I'm going to change this to 1K, 2K, 4K, and whatever. I'm going to pick typical 15 resistors to put here, and I'm going to go through all the measurements of the resistors and the measurements of the voltages, calculate the current, and then I'm going to compare the results to what I just showed you, those three charts. When I do the measurements, which one is correct? When you measure, you're only going to get one result. And when you get that one result, it's either going to show that, yes, it is constant, like modern science says, or it's going to decrease down linearly, not down and then up, just down and down and down. That if that's the way the measurements come out, that means the second one, the TPM equations without speed is the one that's correct. But if you measure it that it goes down and then back up, then it says, yes, speed is a factor in the measurements. The measurements are going to be as accurate as I can make the measurements, and there's no guarantee I'm going to be 100% this way or this way or this way. You do the measurements, you record the data, we'll look at the results. Hopefully within a week or so, I'll have the results to report to you. My name is Bob D. Hilster, and I am your particle guru. If you have any questions, ask Particle. You can email me at particle@gmail.com. Thank you for your attention.